Okay, welcome everyone to this continuation of tropical geometry. What is tropical geometry? Today I have a very difficult name for you. It's actually not very difficult, but it's difficult to pronounce. It's actually not so difficult to pronounce. I'm not sure why I'm whining here. Non-Archimedean fields. And these type of fields are the main players in, well, tropical geometry. So we'll have a look at them. So they're a little bit counterintuitive, but not so different from our favorite field. What is our favorite field? The rational numbers. Well, everyone likes the rational numbers. If you don't like the rational numbers, you're wrong here. Go away. Just kidding. You're free to like whatever you want, of course. So the story starts here. This is clearly a picture of R3, and everyone knows R3. You have 3 coordinates. You can measure like lengths. You can measure angles. A very nice space. And if you just don't refer to it as the vector space, but as a space where you can measure lengths and angles and everything, very often people call it Euclidean space, right? It's a space of Euclidean geometry. Yeah? The standard old Greek angle length type geometry. I guess that's a good name. Angle length type geometry. It's fantastic. Don't call it Euclidean space. Just call it angle length type geometry. And the way people usually do it nowadays is that they use what is called a norm. A norm is a way to measure lengths. Yeah? In geometry, and the standard way to measure length is a norm, and then you can generalize that, because kind of my one of the best examples is, well, maybe your street system goes like that, right? So you have those circles, and then you have this rays going into the middle. Maybe that's how your streets look like. Sometimes they had that when whatever a castle was in the middle or something. Then if you're here, well, that's a bad color. If you're here and you want to go to the center, you're not using Euclidean lengths, right? This is not really the length, because we need to walk all the way to here and then go that way. So people will... this is an example where the usual lengths will not do. So in this case, you would like to have a different notion of lengths. And people realize that, and that's what mathematicians usually do, is they try to generalize it, and pops out a normed space, or a norm. Yeah, and in all of them, you can do some reasonable form of analysis. You have versions to measure length, you have versions to measure distance, you can define a continuity and whatever, right? So, and really norms mimic that, but they don't need to be the same, right? This one is an example where length is slightly different than than what you usually would think, right? You need to go around those arcs almost all the time here. Right? So normed space, and we will also see normed spaces a lot. And not just the Euclidean ones, because we have this log type geometry, right? Tropical geometry, it's log geometry, if you want. So something needs to change. The log is a little bit strange. It's very nice, but a little bit strange. Remember that we had this valuation, which essentially was a log. Yeah? And how do you get from a log to a norm? You take an anti-log. What is an anti-log? Anti-log. But by the way, I would like to call the exponential function an anti-log. Yeah? That's much clearer. Or the log an anti-exp. Whatever. But anyway, anti-log is taking an x, right? So if you have valuation, this should just be v. If you have a valuation, then you just take the x of the valuation, and you get a norm on your field. The only strange thing about this norm is it is non-Archimedean, right? So that's what we do. We have a log type thing. So we take an x, we get a norm, we get a norm space, we get topology and everything, yeah, continuity and whatever. But our norm is a bit strange. It's not standard, because we take a log. Yeah, we have this funny inequality. A plus b is smaller than the max of a and b, which is usually called a non-Archimedean property. So usually you have it's called the triangle inequality, which is really just saying, let me do it with x and y, because it's x and y up here in my picture. X and y is smaller than x and y, which is the Euclidean one. So x and y, the length of those two, summed up is smaller than, and it's pretty clear, right? The shortest path from here to here, from in this direction, is going along x plus y, not going along x and then y, right? So that's exactly where this equality comes from. So yeah, and in the limit they are the same, but in general not. And now we have a much stronger condition. Yeah, so this is called the non-Archimedean one, which is very different from this type of, well, triangle type inequality. Very different from the Euclidean one. Still, you can still define lengths and all of that, so that's all fine. but somehow your notion of length is locked if you want. Because, well, everything here is locked. We're doing tropical geometry. Everything is locked. Huh? It's kind of interesting. So these are called non-Archimedean fields. Whenever you have that, you take a valuation, and yeah, you can get a non-Archimedean norm. And the standard example was actually not a log, but this is also a log, by the way. So if you know p-adic numbers, if you don't know what p-adic numbers are, don't worry too much. They appear everywhere. They are like the following idea. Let me just briefly say that. So the notation is PQ. So what we do here, usually what you do in analysis, tropical geometry, wherever, you study polynomials, right? You study polynomials. But then you realize that you kind of need limit polynomials at one point, which are really just polynomials power series, where polynomials have arbitrary large exponents, right? Something like 1 plus x squared plus ... just all of them together, something like that. The exponential function, for example, has an expression like this. And now p-adic numbers are essentially just, okay, write your numbers, your usual numbers, base p, okay? That would be a finite expression of that type. That's a polynomial, just p is, x is now p, and the p-adic integers are essentially just, well, the power series version of that. If you don't know what it is, it will not appear in tropical geometry. Don't worry too much. But it's a kind of the standard example where you get a non-Archimedean norm. And it's exactly the same process, right? So the p-adic valuation is essentially defined by the maximal number of p to the n divides a. We want the n. So how do we get the n if you look at how often p to the n divides a? Well, you take a log. There's your log, right? If you want to get n, you take the log, essentially. And the p-adic norm is given by the other way around. And yeah, so that's the kind of the standard example. And it's exactly the same, just the log comes in because you look at the number of times p to the n divides your favorite number. So this is where all this non-Archimedean stuff comes from. And if you Google non-Archimedean, this will be the key example you'll find. And I would like to encourage you to look at it and then ignore it, because would you like to learn tropical geometry, where you probably don't need it all that much. Anyway, this is like the historical first example, I think. The one we are really interested in is sum of first, but people have never phrased it like this before and then phrased it later. Anyway, just for completeness, here is the formal definition. And the only thing that is somehow different from the previous slide is essentially nothing is different from the previous slide. What am I saying? Essentially nothing is different from the previous slide. So just summarized here, right? The non-Archimedean property. And the examples that we really want in tropical land are rational functions, where the valuation is a degree of the rational function. Or more general, those power series type objects, where the valuation is given by looking at the minimal degree. So whatever, it could be somehow a power series. Let me just pull it up. It's called I can't, by the way, I can't pronounce that. Poisson series, but we'll see how that goes. So let's see. Let me give you an example of what we are looking at. We're not looking at this city in France or whatever that is. We're looking at this thing, and it's very nice to see an example. Okay, it's something of that form, right? And you just take the most negative power, and that's your valuation. It's a degree thing on those generalized power series. Here you can see that they're generalized. They have, non-integer coefficients. And let's just see how to pronounce this name. Poisson? Who knows? Who knows, really? Sorry for slaughtering all the names. But anyway, so this is really the valuation we are considering. This is really the norm we are considering. Just taking the lowest degree of a power series expansion, if you want. Excellent. So this is like the thing that turns up in tropical geometry. And then somewhat also not. So our favorite series here, which I just call P series from now on, is something of that form, right? So we just have seen it. I can just pull it up again. Oh, no, not that one. We can just pull it up again. Yeah, so it's a kind of an infinite expression. So in particular, it's a little bit difficult. You usually can't write it down using a finite amount of information. So this is somewhat bad for computations. And tropical geometry should always have an eye on computations. So what you usually really just study are rational functions, or kind of completions of rational functions, if you want to store them. But some other, it's like with the complex numbers. You in general can't write down a complex number. The general complex number, you can't write it down. But you still use the symbols somewhat to make your theory nicer. And here's the same. We use the p-series to make our theory look nicer, but in reality, we only work with rational functions, right? In reality, a computer will never work with complex numbers. A computer will work with float point integers or something like that. And it's kind of the same type of trick that we are going to use. Anyway, I hope you enjoyed this video, and I also hope to see you next time.